Hello, have you ever wondered why, when lifting a load, the accessory angle really matters? Perhaps you understand it, or maybe you're even able to calculate it, but haven't actually seen the tension. Well, my name is Kevin Bennison, and I'm the lead lifting operations trainer at InspHigher. And with the help and support of Radius, we're going to demonstrate how the sling angles and indeed variations to the length of the slings will actually impact the tension on the sling legs. We'll be lifting a couple of different loads, and we'll have a load cell on each of the sling legs so you can actually see the tension on each leg as we change the configuration slightly. So let's get started. Here we'll have the first load that we're lifting, which is a 2-point lift, and we've lifted this on a spreader beam with vertical legs just simply to show what the total weight of the load is. Then we can change it to an angled assembly to see how that impacts the tension on the individual legs. As we can see then, from the load cell, the total weight of this load is around about 3,525 kilos, 3.525 tonnes. What we see here then is the left load cell, it's reading 1,650 kilos, and on the right it's reading around 1,870 kilos. Now this is a load that is supposedly a balanced load as stated by the manufacturer, and still we'll have some discrepancy from one side to the other. On the leg that's taken the greatest share of load there, it's around about 53% share of load and 47% on the other side. So there is a slight difference in terms of the loading to begin with. What we'll have here now is the load lifted on an angled arrangement, and the angle is approximately 30 degrees included, therefore around about 15 degrees from the vertical on each leg. Now, if we look at the tension in the leg, and we'll use the right hand leg there as the reference, and that started off at 1,870 when the leg was vertical. We can see there we've now got a load of over 1,900 kilograms at that 15 degrees from the vertical. When we do the calculation then for this lift, we're doing vertical tension divided by cosine of the angle from the vertical. So in this case, 1,870 was the vertical tension. We're going to divide that by cosine 15, and that gives us 1,935 kilos. So that's approximately what it's shown us on the load cell there. It's there or thereabout. Let's increase the angle then. What we'll have now then is a 60-degree included angle. That gives us an equilateral triangle. Therefore the legs are approximately the length of the distance between the two connection points. And that is, of course, a 30-degree beta angle, 30-degree angle from vertical. If we look at the tension on that right leg this time, we've got 2,130 kilos approximately. When we do the calculation, that 1,870 divided by cosine 30, that gives us 2,159 kilos. So we can actually see by doing the trigonometrical calculation, it's getting us very close to what the load cell actually tells us. And that's of course just going to be out slightly with some discrepancy on that accurate length there. This time we have the slings at around about 90-degree included angle. It's actually slightly less. And we can check that simply by holding something up with a right angle, just get side on to the greatest angle of the load and just compare it against it. So we can see that we're doing that here with this booklet. And we're just inside 90 degrees. That means we're just within 45-degree angle on each leg from the vertical. So again, if we do our calculation, and we'll go around about 44 degrees on our calculation, 1,870 divided by cosine 44, that gives us 2,599 kilos. we're actually on the load cell showing around about 2,450. So there's just a slight difference with our calculation and what the load cell's showing. Probably with it being just inside 90 degrees rather than bang on. But anyway, it does show us that difference where we started off at 1,870 kilos at the vertical, we're now at 2,450 kilos approximately. So let's increase the angle again. So the last one for this demonstration is we have picked up here and we are close to, not quite on, 120 degree included angle. So we're really getting up to that maximum permitted included angle. So therefore close, but not quite on, 60 degrees from the vertical on each leg. And look at the impact that's had on the tension. That's now very, very close to double that original vertical tension. So we started off with around about 1,870 kilos. We're using that as a base figure. Then if we divide that by cosine of, let's say 58 degrees, we're not quite on the 60. So 1870 divided by cosine 58, that gives us 3,528 kilos on our calculation. And as we can see on the load cell, we're looking about 3,570. So we're likely somewhere between 58 and 59 degrees from the vertical on that leg. And we're very close to double the vertical tension. So once we get up to 60, you're actually bang on that, double that vertical tension. And this perfectly demonstrates why 90 degree included angle is our maximum recommended included angle. We don't go beyond that unless it's absolutely necessary, our accessories are rated, our load can withstand it, and the lifting points can withstand it. But we would only ever go up to 120, absolutely maximum, and that would be if it was necessary and everything was rated to cope with that. That just perfectly demonstrates why we stick to those angles and the impact those angles will actually have on the tension on our sling legs. So in this case, we've now got a 4-point lift and we have 4 legs of even length. We're around about 60 degree included angle there. And what we're having a look to see is what the loading is currently on all of those legs. Looking at the load we have on each leg here then, we can actually see that even though it's an evenly balanced 4-point lift, we don't have even loading on each of the 4 legs. Actually, 2 of the legs are taking far greater load than the other 2. Rather than 25% share of load on each of the 4 legs, what we've actually got is the heaviest leg is taking around about 31 to 32% of share of load on that assembly. This demonstrates to us why, when we're using a 4-leg assembly, for onshore lifting operations, we'll only ever rate a 4-leg assembly the same as a 3-leg. Because even though we can seem to be achieving even loading on each of the 4 legs, we will not actually achieve that. Let's actually change the length of the leg slightly. We're just going to reduce one leg by 1 link in length and see how that impacts the loading on each of the 4 legs. So on this load, what we've done now is we've actually shortened one of those legs by only 1 link, just to see the difference of the share of load. And if we have a look at our loadings on the load cells there, we can see now that basically 2 of those 4 legs are pretty much taking all of the load. There's very little on the other 2 legs. With doing the calculation then, just to work out what share of load we've got, the leg that's loaded the most there is taking around about 49.5%, 49.4% of the weight of that load there. So we can see just by changing the length of the legs very slightly, we're really in danger of potentially overloading the legs here. So we've got to be really careful when we're shortening legs on these multi-leg arrangements. Okay, so there we are. What we've demonstrated in this video is that as the angle increases of the accessories, Of course, the tension then increases in those accessory legs, which includes all of the accessories in that arrangement. So we've got to consider shackles within that, anything else that's within the leg. And of course, as the tension increases, the resulting safe working load or rated capacity will actually reduce. The amount of load we can safely lift will reduce as a result. This also shows us the reason why the maximum recommended included or internal angle is 90 degrees. The maximum recommended vertical or external angle is 45 degrees. The maximum permitted internal angle is 120 and the maximum permitted external or vertical angle is 60. We had a look at 4 leg arrangements, and that even though they appear evenly loaded, it's very, very unlikely that a 4 leg arrangement will be equally loaded or evenly distributed. So therefore, a 4 leg assembly is only ever rated the same as or as much as a 3 leg, because often that distribution throughout the legs will be different. And we also saw that when we reduced the length of one leg by even a tiny amount, it hugely changed the load distribution on those 4 legs. In fact, then that shortened leg was taking close to half of the load. Hopefully you found that video really helpful. If you'd like any more information about all of those who have been involved with this video, you can go to tractel.com for more information about the load cells. You can go to radiusgroup.co.uk for more information on the services that Radius provide. And of course, for training and mentoring and consulting from InspHigher, it's inspire.co.uk. Thank you very much. And as always, keep inspiring.